you guys can see this cylindrical and spherical coordinates. And this is actually the last section of chapter 11, okay? Cylindrical and spherical coordinates, which means the rest of the week, we have 2 more classes. I know there's a group quiz day, there's a classwork day, take-home quiz and all that. And then next Monday will be your chapter 11 unit test. So using cylindrical coordinates to represent surfaces in space. So we've talked about various surfaces in space now, all of, which we talked about all of that in rectangular. There's certainly many cases where using a different coordinate system would be preferred. We'll make it easier. Okay, again, we're introducing different coordinate systems to make our math easier, not harder. Okay, I would only use cylindrical or use spherical when it makes sense to do that. Cylindrical is really just your 3D polar. Okay, so think back to polar, right? Your r comma theta. Theta is your, remember, if theta is positive, it's your angle counterclockwise from the x-axis. R is your directed distance from the origin, okay? And if it's cylindrical, we're gonna add a z coordinate to it. Okay, so these are just a few slides I pulled in from Calc BC in terms of, reminding you how we graph in polar. Because, okay, and you guys know, right, there's multiple representations when we're talking polar. Whoa. Okay, this picture is not great. I really need to change this one. Let's go to a better picture. Okay, I think this is better. Okay. So our cylindrical coordinate system is represented by r comma theta comma z. Okay, so your first 2 coordinates, the r and theta, that's just polar, right? If it's in 3D, it's polar. And then we're adding this additional z component if we're in 3D. So go to our 3D picture. Okay. So here's rectangular. This point is XYZ in rectangular. In cylindrical is r comma theta, and here's your XY, right? So think polar on the XY plane. And theta, if it's positive, again, you're going counterclockwise from the x-axis. So if theta is positive, you're going from the positive x to the positive y-axis, right? Here's theta. And then here's r, okay, and then z, okay. Yeah, so cylindrical is not bad at all. If you understand polar, all we're doing is adding another component, and then kind of makes sense if you think about the cylinder, right? I'll show the other representations in a bit. So if you're doing conversions, z is just z, right? This x, to do this conversion, just remember the right triangle that we used to draw to do polar conversions, right? Here's r, here's your right triangle. X, of course, is r cosine theta, y is r sine theta, and then z is just z, okay? For both cylindrical and rectangular. Okay, here's our conversion routines. Not a surprise at all if you remember polar. And so, let me see. Okay, it's showing some of the conversions. Again, this looks like exactly like polar, right? The more interesting one is the spherical. Okay, let's erase this. So here's some shapes that you could, some quadric surfaces or cylindrical surfaces that might make some sense to use the cylindrical coordinate system. Okay, so in the rectangular coordinate system, if this is in 2D, that's just a circle, right? In 3D, this is missing z, right? So you can see how if it's in 3D, you've got x squared plus y squared is equal to 3 squared. Oh, that's a terrible trace. Okay, it's a circle. Okay, I'm trying to draw the trace on the XY plane. Okay. Now, if you take that trace, oh, that's terrible. Okay, so here's my circle with radius 3. That's still bad. Okay. Okay, and it's missing the z. And remember, missing the z means that z can be anything, right? So you take that circle, and we also describe this cylinder as, the collection of all the rulings, right? Okay, where z can be anything. So this is how I would think of it in rectangular. Okay, look at it in terms of in cylindrical. Cylindrical is really easy. In fact, that's what this cylindrical coordinate system is made for. Okay, stuff like this. Okay, R, regardless of, there's no theta because it doesn't matter what theta is, right? Regardless of what theta is, R is always a distance of 3 from the origin. And Z is missing. Z can be anything, right? Okay, so that's the easiest shape to do a cylindrical coordinate system. If we're dealing with this one, now you see that, oh, R is a function of Z, right? When Z is equal to 0, we are the origin. As Z increases, R increases. Okay, that is in fact a function of, and if you square both sides, right, you can see how we get from the rectangular to the cylindrical or vice versa. R squared is equal to 4Z, and R squared is x squared plus y squared, right? You can see how you can go from one system to the other system. Okay, so both are, I think both are fine, right? Rectangular or cylindrical. Here, x squared plus y squared is equal to z squared. We've got our elliptical cone. I think this is a much nicer representation, a cylindrical. R equal to z. Yeah, it says that when z is equal to 0, R is equal to 0. As z increases, right? As z increases here, your radius increases. Yeah. Okay. So let's see. And similarly, this hyperboloid, okay, x squared plus y squared is r squared. Okay, so you can see the various representations. Okay, so now you have an alternative way of representing these quadric surfaces. Vertical planes. You've got planes here that are a function of theta. When theta is equal to a constant, you know, theta is equal to c, yeah, that's a plane. Here, R can be anything, Z can be anything, right? Just the theta that's fixed. Okay, so yes, that's a plane at theta equal to c. Here, if Z is equal to c, well, that's the same as rectangular coordinate system, since Z is a part of cylindrical as well as, okay, so that's the easy one, okay, cylindrical. Okay, let's go to spherical. Okay, for spherical, it's really nice to have this sketch. In fact, McHill, you can see this is my, okay, there's a student that did a presentation on cylindrical spherical and they cut the styrofoam ball and drew the coordinate system inside, ooh, trying to turn it the right way. Okay. Okay. Yeah, that's a styrofoam ball that a student did, etching this sketch into that styrofoam ball, okay, to illustrate spherical. So for this to make sense, draw in all the right angles. Because again, my claim is that you can prove all of these conversions using Pythagorean, okay? So your spherical coordinate system, cylindrical was easy to remember, right? Cylindrical is really just polar, okay? It's r comma theta and then add a z dimension, okay? Spherical is rho and then theta, okay? And phi. Now that phi can be called phi or phi, okay? I've been calling it phi, but I know many places call it phi. So let me write this a little better. Yeah, that's rho. Okay, so rho theta phi. Okay, phi or phi, okay, whatever you want to use. Now, these two are both angles, and rho is the distance, okay? So your theta is what you know theta to be, okay? The same theta as in the polar coordinate system or cylindrical coordinate system, okay? The angle from the positive x-axis on the xy plane. Your rho is the directed distance from the origin. So right here, okay, that's rho. And then phi is your angle from the positive z-axis. Okay, so now if you draw all of the right angles, it'll help you to understand this picture. Okay, so you can see kind of the 3D. Can you see that actually? Make this a little bigger. Yeah, I normally draw this on my whiteboard. Sorry, I didn't do that for you, Nikhil. Okay. Yeah, I find if I can draw this picture, then I can come up with all the conversion things without memorizing anything. Okay. So this is, that's a right angle. This is, what is that, phi? Okay, so if this is phi, then this is also phi. Oops, sorry.
What is phi again?
Phi is the angle here from the z-axis. Yeah, from the positive z-axis. So this is your point, right? Okay, so draw that, yeah. So here's phi, which makes this also phi. Right, that angle is also phi, right? Okay, so if you can like visualize that, okay, I really do feel you can come up with all the conversion routines. So R is equal to, right, look at this, R is equal to, and that's where if you write V up here, then you can come up with this conversion routine. R is equal to, its opposite phi, right? R is equal to rho sine phi. Yeah. And R is also, if you use rectangular or cylindrical, R is also equal to x squared plus y squared, right? If you look at this right triangle, because this is x and this is y. Okay. Yeah, is that making sense? So for example, so the sphere, right, our Earth, okay, the point on the surface of Earth whose latitude, you see these coordinates sometimes, I don't know, on GPS or something like that, you see coordinates like that. So here's theta, this would be, is this rho? Yeah, this is rho, right? This rho, and this is theta, the angle clockwise from the prime meridian, and this is the angle from the North Pole. Yeah, so that would be your phi. Right. So yeah, I think you might see this somewhere on GPS or something, these spherical coordinate systems. So again, here's a description of all of those. Okay. Rho is the distance between P and the origin. Phi is the angle between the positive z-axis and the line segment OP, where O is the origin and P is your point in your 3D surface. Okay. Okay, and we even spell it out for you. Okay, if you forget how to write that, practice writing this rho. Okay, don't write it as a P. It's not. Yeah, it's not P. Okay. It's, yeah. So now our conversion, ooh, this is a bit of a mess here. Let's write this up. Okay, here's our conversion routines. But let's see if we can make sense of this. Okay. See that? Okay, so if you look at the appropriate right triangle, okay, X, you guys know from polar, X is equal to R cosine theta. Right? Okay, now what is R? Okay, because I'm trying to convert it to spherical. R is not, sorry, to spherical. Okay, and spherical, R is not part of spherical, right? R, if you look at this right triangle over here, just draw your right triangle here, R is opposite phi. So R is equal to rho sine phi. Yes? Okay. So this complicated looking thing is just R cosine theta. Yeah. Where R is equal to rho sine phi. And again, that's if you're looking at this right triangle right here. Okay. And then Y, of course, is R sine theta. Okay. And Z, if you look at Z, this is Z. Okay. Oh, there you go. Oh, you didn't even have to do a dance. Okay. Z is equal to over here, right? if you look at phi, z is adjacent. So z is equal to your hypotenuse, which is rho cosine phi. Is that as clear as mud out there? Yeah. Trying to see a sign of, are you guys getting it out there? Okay. I'm just gonna look at you, Nikhil, does that make sense? Okay. Yeah. Okay, so rectangular to spherical, or rectangular is x, y, and z, right? So rho squared is equal to, we're using our three-dimensional Pythagorean, right? Okay, which we've done before. And this, if you want to just look at one right triangle at a time, well, sure, rho squared is equal to r squared plus z squared. If you look at just this right triangle, and then convert r squared to x squared plus y squared. Tangent theta is equal to y over x. This is just polar, right? And phi is our cosine of this whole ugly thing, but really this is the same thing as phi is equal to, an easier way to look at it if you want to just look at one right triangle. Here, let me write it up here so it doesn't cut out. Okay, this is equal to arc cosine of z over rho. Yeah, phi is equal to z, the adjacent, look at this right triangle, over rho. Yeah, rho is the hypotenuse for that right triangle. Okay, okay. And this whole ugly thing is rho, right? Square root of x squared plus y squared plus z squared. Okay, yes, no, okay. Okay, I hope this is making sense. Yeah, I'm used to doing this with my beautiful sketch on the whiteboard and pointing to the various right triangles, but you know. Okay. Spherical to cylindrical, and again, I think if you look at that diagram, what I've done on quizzes and tests is provide the sketch. Yeah, my claim is that if I provide this sketch, you should be able to come up with all the conversions. Is that yes? No? Okay. So that's what I've done on tests. I've actually put this image on there. So if you can visualize that, then it's not, you can come up with these. Yeah, I don't really like memorizing a whole set of formulas. So if you can come up with that or reproduce that sketch, to me, you should be able to come up with each of these conversions by looking at the appropriate right triangle. Okay, so various conversions. Here, these are nice, some nice quadric surfaces where spherical coordinates make sense. First is the sphere. That's like the most obvious, right? Your sphere, remember, is just the set of all points that are equidistant from the center. And that distance, that radius, right, is rho. Okay, I won't try to mess that up. Yeah, that's equal to rho, right? Okay, and again, spherical is rho theta phi. Okay, so we're taking each of the, if rho is equal to a constant, you've got a sphere. If theta is equal to a constant, theta is the angle positive, the angle counterclockwise from the x-axis. If theta is equal to a constant, you've got a plane. Right? Yeah, theta's out here. Yeah, then it's definitely a plane, and that's just like cylindrical or polar if it's 2D. If this one is good to understand, phi, because that's probably the argument that's least familiar to you. Phi is the angle from the z-axis. Okay, phi is this. Okay, so go out angle from the z-axis, and then you extend out rho, out here, right? Okay, so what you have is a half cone, I guess. Okay, does that make sense? So yeah, we're just taking each of the arguments and coming up with a quadric surface. So all three of these kind of make sense in cylindrical or spherical. Okay. Some of the equations. I mean, this looks ugly, right? but it's really not that bad if you think this whole thing is just r squared cosine squared, right? This thing is r squared sine squared. Wait, is that right? R sine, wait, what did I have as my r? Yeah, r squared is square root of rho squared sine squared b. Yeah. Okay.
That's for converting from rectangular to spherical, right?
This is going from, yeah, rectangular to spherical, yes. Okay, so yeah, so this is, and then of course the cosine squared and sine squared is equal to 1. So this whole thing is just r squared. This whole thing is just r squared. Okay, and then this is z squared. Okay. Oh, it's all out here. Okay. Is that it? Circle form. I'll leave these for you guys. Note the solution set for the equation includes a point for which rho is equal to 0. Okay. Okay, I think that's it. Okay, so take a look at your. So on today, WebAssign should already be open. Is that correct?
That's open.
Okay, so you have a choice of WebAssign is due tomorrow. So if you want to start on WebAssign, that's fine. If it helps you to do some warm up first, that's fine. The warm up will not be due tomorrow. Okay, you can go ahead and start it. I'll make it due. I can't remember, sometime this week. Okay, but so you have 20 minutes. Okay, if you want to spend that time to work on WebAssign, that's totally fine. See if there's anything I need to do for the ones. Yeah. Any questions? If not, we will move you into breakout rooms. You get to be part of a group with me as well as the virtual breakout room. So, okay.
Miss Shack, I can't open the warm up on the lesson plan.
It's not.
Oh, really?
It's not hyperlinked.
Oh, okay. Let me do that first. You find sometimes it's helpful to work out a few first before you do WebAssign. Okay, I'll do that right now. Thanks for letting me know, Gavin.
Oh, and also you can probably stop recording.
Oh, by the way, today is Tuesday, which is Puzzle Club Day. Rohan and Parth, I'm doing an announcement for you guys. One of you want to announce Puzzle Club to the rest of the class?
Oh yeah, you guys should join Puzzle Club. It's really fun. We solve puzzles after school. Yeah.
Okay, where do they go? What time? All that stuff.
Yeah, so it's in we have like a separate Zoom room, so like you guys can just like email me or Parth if you guys want to like be sent the link. It's after schools on Tuesdays from 3:30 to 4. Yeah. So hope to see you guys there.
Okay, all right. And I think you guys even have some competition coming up, right?
Yeah, we have a $50 Rubik's Cube competition. So if any of you guys know how to solve one, we don't have any submissions yet. So that means that if you guys like send me a video of you solving it, you guys could win $50.
Whoa.
So yeah.
Cool. Okay, it should be on there now. open up the breakout rooms. Oh. Neil, thank you. Yes, I should stop recording. Okay.